Good morning, everybody. This is George Follendorf, and what we're showing here is the agenda for today's topic, and TWT versus a modern solid-state architecture. But it's I want you to know this is not just the typical TWT versus solid-state discussion, and further, it's also a modern solid-state architecture versus traditionally architected solid-state amplifiers. And how we'll start off is with a little overview about the company and how we got here, the evolution of the product to where we're going in today's discussion, the scalable liquid-cooled amplifier. I'll move through that quick so we can get to the meat and talk about the major system elements, and Paolo will get into some detail there for some very interesting stuff. We'll talk about scalability and availability, and then a fallout from availability is the concept of effective MTBF. That's a pretty interesting topic. And then with all of that understood, we'll hit up total cost of ownership. So for those of you who don't know, SMPower RF is an established supplier of solid-state power amplifiers to the DoD, prime contractors, and commercial companies with applications that include tactically deployed communication and jamming systems, amplifiers for radar, open air range, signal environment simulation, and other training systems, and amplifiers for test and evaluation systems, directed energy, EMC, RF component testing, and others. And the configurations include COTS modules, air-cooled systems, and liquid-cooled transmitters from tens of watts to hundreds of kilowatts. Now, our existing lineup of air-cooled systems are known as multi-mode and interoperable power amplifiers. But without going into detail, I'll just say that, an interoperable multi-mode amplifier is an amplifier that can operate in any mode across multiple applications without a change in hardware. So it's a very flexible amplifier. And we're extending our multi-mode functionality of the air-cooled architecture with even more high-speed computing, which is necessary for combining large arrays of amplifiers, as you'll see. Now, what's driving the new technology, and the images on these slides, these are ads you might have seen in Microwave Journal or Journal of Electromagnetic Dominance. But what's driving the need is the need to dominate the electromagnetic battle space. In other words, be better than adversary technology. On the far left, the desire to increase transmitter capabilities, for example, multifunction radar. What is that? So that's a single emitter system that primarily operates as radar, but can also jam or communicate. And then in the top right corner, with the proliferation of satellites, the high data rates are being asked for, on top of lower cost of ownership and higher availability. And then the bottom right-hand corner, more generally, is the trend of replacing of an aging TWT infrastructure. Yeah. So here's some examples already of some air-cooled systems that are replacing TWT, just to give you some context of where we're playing right now, that we're evolving to even the higher power systems. So in the left, threat simulation systems, these are pulsed amplifiers. So there's a 12 kilowatt VHF, 12 kilowatt pulsed, 10 kilowatt pulsed in S-band, 8 kilowatt air-cooled in C-band, and 8 kilowatts in X-band. All of those are long pulse width and duty cycle.
And George, what do you mean by long pulse width and duty cycle? What is unique about that performance?
Well, first of all, it's difficult to do in a TWT. So the TWTs that are available don't offer that. So in solid state, we're uniquely positioned. Paolo could probably explain what it is that we do differently, but I'm talking 20% duty cycles, for example. That's what I mean by long pulse.
20% duty cycle.
And 550 microseconds pulse width.
Okay, got it. So I just want to talk about the benefits up front. We could dive into the technology and hit benefits later, but I prefer it this way. And then the technology kind of fits, it makes more sense. But beyond GaN, beyond the semiconductor device, and beyond operating class, the architecture matters. And by building out the right architecture, there's meaningful improvements in reliability and availability, which we'll talk about later, signal fidelity, waveform flexibility, total lifetime cost of ownership, and system integration features and scalability. But final word on evolution. Moving from the air-cooled family to the liquid-cooled, the RF deck is consistent. So we're using the same RF chain in this architecture I'm about to show you, and that RF chain is established, it's proven, and it's fully characterized. So what we're doing is wrapping new technology, better technology around an established RF chain.
I think not to be lost in this for everybody, the RF deck on the left-hand side, you see it's an air-cooled RF deck, and what that means is below this RF structure is a heat sink with long fins and fans to provide air cooling. That identical architecture in terms of the driver and output pallets and pallet combining, embedded computing, that same architecture has been put to use in a liquid-cooled deck. So obviously this is 2U chassis, and that's a fully integrated amplifier. This one on the left-hand side is probably a 5U chassis. So not to be lost in this whole thing is that platform-driven approach. So, and I know George has got a lot of material here shortly that talks about one versus the other, but at the end of the day, for us internally, the breakthrough is in eliminating every cable and connector, not spilling tenths of dBs anywhere in this RF combining chain. And that is how we achieve the power densities that allow us to do some of these very compact systems.
Yeah. And here's a visual of the system, a scalable liquid-cooled amplifier. And the implementations here are usually broadband and CW or pulse. It's liquid-cooled for power density reasons. For example, an equivalent air-cooled system would be about 2.5 times larger. The amplifier consists of a controller in a 3U form factor, and in this case, 16 modular amplifier building blocks, 2U in size, and are fully integrated amplifiers in their own right. And we'll talk in some detail about that in the upcoming slides. Rounding out the major elements of this 6-foot-tall chassis is the liquid cooling distribution system shown on the right. And then there's a 16-to-1 combiner that's integral to the rack. But stay tuned. It's not shown here, but a detail later, and Paolo will talk about that. The lower left image is the backplane, where each of the 16U modular 2U amplifier drawers slide in and out, blind mated to the rest of the system. And finally, I should mention that not shown is the external pump system and heat exchanger for the sake of brevity. So now just going into a little more refinement, a little more detail, the fully integrated liquid cool amplifier building block, you can see the pop out in the image, is the foundation of scalability. So each 2U chassis is a fully functioning, this is important, a fully functioning integrated amplifier. In other words, full gain, no external driver, and power supplies are integrated underneath the RF deck. So a system level power supply is not required. The system controller, that's the 3U with the LCD screen, incorporates our high-speed embedded computing architecture to ensure precise control of the individual solid-state amplifiers in the transmitter cabinet, as well as maintaining control of the overall system. And the backplane connections and mechanical interface design ensure dripless liquid cooling and hot swap capability for replacement of the individual 2U chassis. And I should say one thing about the combiner. The combiner is configured based on frequency and the number of 2U boosters. In this case, it would be a 16-to-1 combiner. So here is the RF deck, also known as the booster. The engineers here like to call it the booster. So you'll hear it referred to both ways. So this 2U RF drawer has a 1 driving 4 in parallel configuration. We're following a 4-to-1 waveguide combiner that terminates the blind mate connector. The amplitude and phase is controlled digitally on board. And you can also see in the drawing, the cooling ports in and out. So let's talk about points of failure. Yeah, in this architecture, availability is much higher than TWT. So for the TWT, the tube, the power supply, and the tube driver stage are single points of failure. And traditional solid state designs also have several points of failure. And for mission critical applications, it's crudely solved in some cases with a redundant system and a baseball switch. Now, let me explain how this always on air works. This 1 driving 4 arrangement, if a pallet goes down, the 1 driving 3 section continues to operate with the output dropping fractionally. If a driver fails, the driver driving 4 pallets, then the entire drawer fails. But in either case, the system is still putting out power with only a fractional loss. So a little bit later, I'll show you a table that illustrates the transmit power with the failures. That's pretty interesting.
And George, just to back up 1 slide, I think for everybody, what George is describing is depicted here. You lose 1 2U, you do not lose that cabinet. And so there's not a single point of failure from that standpoint. Each one of those 2Us is a fully integrated amplifier. So there's not a separate large power supply, not shown in the picture that if you lose that, you lose the whole thing. So, and go ahead, Paolo, you want to build on that?
Yes. One of the important things is why did we design it that way? Okay. Having a backplane, having integrated power supplies allow us to, in case of failure, take the complete drawer out without having to go to the back and disconnect RF cable, disconnect AC cable, disconnect blanking cable. So it comes out without having to do more than take 40 screws on the front.
4 screws, yeah.
Yeah. Okay, then you take the amplifier out, you put another one in probably 5 to 10 minutes, you are back with full power. Okay?
Yeah.
So the structure that was built on these amplifiers or these amplifier systems allow you to have a very quick time to repair and makes it, although it's more complicated in terms of design, it's much more simple to do operation, to operate it. Okay?
Okay. So Paul is going to talk about the digital features in the transmit. I just kind of want to set something up a little bit. You see that diagram on the left? That's a classic digital pre-distortion circuit. That's what we're moving towards. So the traditional amplifier is an open loop. We've closed the loop with our air-cooled system, and then we're closing the loop even tighter with this liquid-cooled system. Paolo will touch on that. But beyond that, there's new technology that creates digital functionality within the amp. You want to take it from there?
Yes. Okay. The advantage of combining digital with RF is the capability to correct the errors existing in RF amplifiers. The idea is that let's put it in class AB, let's make it more efficient and correct the errors digitally. There are 2 ways. One that we have already implemented, okay, and we are in process of qualifying, is to correct the pulse. Okay, so I have an envelope that I detect out the output, an envelope that I detect in the input, and I do exactly what is in these block diagrams. I compare one to the other. I create a lookup a lookup table, and I correct the droop or ring on the pulse, okay, using that kind of feedback. That's one thing that we already have, and we are in, that is, the code is developed, it is loaded in the FPGA, and we need to do qualification for that. The second aspect of it is a possibility of correcting linearity. Okay, this we have conceptualized, we have not started yet, and the block diagram shows that. The idea here is that because DACs and ADCs today can go to very high frequency, okay, in gigahertz or gigasamples per second, and because I can interleave them, which doubles the frequency, okay, I can take the input signal, convert it digitally, okay, as well as convert it digitally, the output signal, and operate in the fundamental frequency of the that is being transmitted. Okay, in the past, the pre-distortions and digital signal processing was done in baseband or in IF, but not in radio frequency. Our approach is that because we do only the amplifier, we don't do the exciter, okay, I want to correct my amplifier and provide it with full, complete linearity, okay?
Here you see images of the Cband Combiner and a UHF combiner for two different scalable liquid-cooled applications.
So the important things here are few important things. First, the combiner has to have a blind mate connector for the boosters. Okay, we don't have any cable between the booster and the combiner. So it goes straight and excites the combiner from the output of the booster. That's one important thing, okay? The isolated loads, combining two racks allow me to use the isolated load or isolated attenuator to feed back to the control and see the error of phase and gain between racks. Or within a rack, I do the same way, okay? So instead of, if I have 16 in a rack, instead of combining 16, I combine 8 and 8, and I have a 3 dB hybrid or a mesh KT to make the final combination of the 8 and 8, okay? Since hybrids and mesh KT have an isolated load or an isolated port or an isolated attenuator, in our case, we use an attenuator and we feed back to the controller, and the controller adjusts the gain and phase of the array of amplifiers so that I minimize the power that's being dissipated in the isolated load. And last is if I have a VSWR fault, okay, because I operate in FPGA time, we protected the system in few hundred nanoseconds, which allow me, for example, if I have an arc in a waveguide or an arc in a coaxial cable, I do shut down in few nanoseconds, hundreds of nanoseconds. I shut down, which cuts the arcing, okay, and then I take a little bit of time and turn it back on, okay? So that guarantees that the arcing is not sustained, okay?
And I think just taken to another level in terms of the scalability, this last example, George, is 4 cabinets put together.
Yeah, 4 cabinets, and this is an actual system we can build. This was in response to a request for proposal. But what you're looking at is a 4 cabinet system, 2.9 to 3.5 gigahertz at 310 kilowatts peak power, 16% duty cycle. So it's 7 foot high, 8 feet wide, and 4 feet deep. Now, there's 3 levels of scalability, and you can start anywhere in these 3 levels of scalability and arrive at this 4-cabinet system. So we've got scalability at the rack level. You start with 1 rack and you add another rack. In that case, we would have to include with that a 2-to-1 combiner, combining the 2 racks. There's scalability at the 2U drawer level. So imagine a single rack where you might have 10 or 12 2U amplifier drawers, and down the road you want to expand that. So let's say you have 12 2U drawers. That system's going to come with a 12-to-1 combiner. When you want to increase your output power by 25%, you would add 4 more drawers, but then we'd also provide a 16-to-1 combiner. And then there's a third level, longer pulse width and duty cycle. So, down the road, we could provide you with a software firmware change that gives you longer pulse width and duty cycle. And tell me if I'm right or wrong about this. You still have to trade off peak power for average power in that case.
Yes, the issue is the following. The longer the pulse, okay, it approaches the amplifier to a CW operation, which means that you have to back off the power because the device cannot handle that. The advantage of having a smart amplifier is that I can define profiles, and I can say up to 500 microseconds in certain cases, I operate at full power. Okay, sometimes in this case, the Cband, I can go up to 1 millisecond. Okay, and if I need to do, let's say, 2 milliseconds or 5 milliseconds pulse, there is another profile that will back off the peak power, so that's equivalent to the power dissipation that the device can handle. Okay, so I can have multiple profiles and control the amplifier that way, and you just call and say, I'm gonna run at 5 milliseconds pulse, and then the amplifier will adjust itself for that condition.
Yeah, let's talk about availability now. Availability is the period of time a transmitter is not out of service, and on-air availability is maximized with a distributed architecture like this. Since it's intrinsically fault tolerant, you wouldn't characterize it as a redundant architecture. Now, low mean time to repair increases availability, but hot swapping maximizes availability. So take a look at the yellow section of the bottom table here. That's an example of a 100 kilowatt rack with 16 drawers. So in the case, I'm showing the case of when 1 drawer fails or 2 drawer fails and so on. For simplicity, the more likely scenario is 1 pallet out of a drawer would fail, and in which case the numbers are even higher, right? But let's just imagine, say, the driver of a drawer fails or the power supply fails. In this case, the amplifier would still output almost 94 kilowatts. In other words, just 0.28 dB below full rated power. And if 2 drawers failed, 88 kilowatt, and so on. So the benefit's clear for maximizing availability. If your amplifier doesn't operate at full rated power, or your mission is still effective at, say, 0.28 dBm below full rated power.
So George, that's an important slide then. I mean, you're saying the way this architecture is put together, that losing a booster is not game over.
Right.
So you are still, as the operator, got lots of power, and depending on the mission, you may have more than adequate power. Losing, in this case, as many as half of these drawers, you're still on the air with diminished with your power cut in half. But that is remarkably different than if you lose a tube.
Yeah.
You lose a tube, you're done.
And furthermore, okay, the tube is not easy to take out and substitute. You might be out of the air for a day. Okay, you might need a crane to lift the tube out of the socket.
Yeah. So
Okay, so this is not comparable, the availability and the maintenance of a tube and the maintenance of a solid state.
Yeah. And that's, I think, George, your next slide here builds on that a little bit. And there you see it again, the 2U chassis that's extracted in that picture, just to illustrate. That's the repair cycle.
Right. So with always on air availability, the concept of effective MTBF comes into play. So the idea here is that you have X total units operating in parallel, and you only need Y units operational to meet your spec or achieve your mission. So in that top row, let's look at the MTBF, the second column from the right. 20,400 hours for a single 2U drawer. That's an actual calculation for mill standard HDBK 217F parts count method. Now moving over to the right, you see number of parallel units. So this is a 16 drawer system. So if you extend that MTBF all the way to the right, you get 1,275 hours. Yeah, that's a small number, and it's small because of the enormous parts count. So that top row is signifying, if there's any component failure in the amplifier, game over. 1,275 hours mean time before failure. But how you overcome that is with the architecture that we have. So the same booster, 16 of them in parallel. But you look at the MTTR, mean time to repair, we put in a half hour here. It's shorter than that. Probably takes you 15 minutes maybe to find the spare, right? But if the system operates according to requirements, specifications, mission, the effective MTBF is 7 million hours. Now, why is that the case? Well, the mean time to repair is the most significant variable. So what this is saying is that statistically, it's very unlikely that a second amplifier drawer will fail within the mean time to repair window. So I can tell you, I pulled this data off of an online tool that you can find. If you want to know where that is, contact me. And I looked at the math and don't really understand it, but I understand the principle. But I can tell you this: we had a major defense contractor also do their own analysis using their proprietary algorithms based on decades of experience. So their numbers came out very close to this. So yeah, let's talk about the total cost of ownership. I've got a couple slides. There's a graphical model on the next slide. But the major elements here are the initial amplifier costs, the solid state PAs, often higher in cost than the TWT, that's for sure. Reliability is the next major cost driver over the lifetime ownership of the PA. And solid state's got a clear demonstrated advantage again. But again, let me remind you, the architecture of solid state matters in terms of extending its effective MTBF. The mean time to repair is not cost per se, but it's a driver of cost of ownership. It directly affects equipment sparing quantities, and higher MTTR implies more specialized technician service training required. Maintenance costs don't apply to solid state PAs, but they do for TWT, so you can fit that into your model. And then major repairs are not uncommon in either tube systems or solid state designs that are not modular. And you can factor in electrical power costs. I don't do this in this case, but finally, equipment sparing. I'll show you the dramatic effect on that for total cost of ownership on the next slide.
And George, not to lose the warning on the right-hand side, that's the certainly from our standpoint, the ultimate factor is a safety factor. And I don't believe there's any debate about the voltages required for one architecture versus the other. Although we're operating at 48 volts
48 volts.
across each one of those 2U chassis.
Yes.
And
it's inside the box. Okay.
that is
and you don't
certainly-
have access to any
it.
voltage.
Right. And that is certainly not the case. As you see there, those are cut and paste from some user manuals that are pretty stark warning.
And the other thing is that you don't need specialized technicians that are more and more rare.
Yeah.
Okay. How many people know tube and studs tubes in the schools today? Very few people.
Yeah. So George, that all brings us to a model of sorts. Go ahead.
Yeah. Here's a model, and it's all about assumptions that I made, but it's really just here to stress the impact of the architecture. You can take a look at the assumptions made. I'll talk about them in that table in the upper left. But you do have to put in your own TWT or traditionally architectured solid state numbers in there based on your historical data. And your use case matters. So in this example, I chose an 11-year period for total cost of ownership. The example here could be directed energy application, electronic warfare, fixed site, or ground mobile, or radar for that matter. I just took arbitrarily the initial SSPA cost at $1.6 million, and with the assumption the tube-based transmitter is 60% of the solid state price. The other assumptions, the solid state 2U drawer in the scalable amplifier there's one replaced every 3 years. And for the TWT is rebuilt at year 5, and the TWT replaced at year 10. And both the top and bottom charts use the same assumption. So the chart on top just has initial cost is only the price of the transmitters. And you can see by year 10, the lifetime cost of ownership for the tube system is 30% higher than the modular solid state. Now on the bottom chart, same cost as above, same assumptions, but the initial condition is buying a spare system for both the TWT and the solid state. So in the case of the solid state transmitter, a complete spare system consists of a single 3U controller and 2 spare 2U amplifier drawers. So the initial costs are nearly the same, and in the end, the tube solution is 60% more expensive than the solid state. And on top of that, on top of the cost savings are the intangibles. The scalable system never went off air. The technician training is greatly simplified, and safety is improved.
Pulse width, duty cycle.
Performance.
Performance.
On and on.
Yep.
Yeah, and. So I might as well then conclude with just a summary. The lower cost of ownership is greatly improved. Extreme effective MTBF. The system's upgradable. It's an always-on air architecture. We didn't go into detail on this, but the pulse fidelity, pulse capabilities include random duty cycle and pulse widths. Waveform flexible, as is still the case with our air-cooled systems. Signal processing functions on the roadmap, and swap is better in many cases. Features there for integration benefits, and then the long list of intangibles. So I'd like to thank you all for tuning in. And Ryan, do you want to take it from here?
Yeah, absolutely. Thank you, guys. Well done. You really covered a lot there in a short period of time, and it was really good. So thank you to all of you, George, Paula, John. It was great. We're open up for Q&A right now. So there's a question box where if you want to type in your questions, feel free to do that. We also I've uploaded a PDF version of the slides that were used in today's presentation, so you can download that directly from the handout section of the webinar. And just as a reminder, I will also be sending out a follow-on email to all attendees and even those who were registered but didn't attend, so they can watch this video on demand as well as get all the resources that were provided. So with that, we've got some questions here. Let's start at the top here. What device technologies are you leveraging, and does the device matter?
In terms of the architecture, no, the device technology doesn't matter. We are using LDMOS and GaN for most of our transmitters, broadband transmitters.
Yeah, I'd say, and without speaking in absolutes, LDMOS for us is probably 1 gigahertz and below, and then gallium nitride on silicon carbide is device selection once we're above 1. And the work we're currently doing is, I think George mentioned at the outset, we're going from HF to X-band with our portfolio. And the current designs that we have with the scalable architecture, those are predominantly UHF, VHF up to C-band, and then actually we have an X-band design as well that's air-cooled, not liquid-cooled. But long answer, short question, LDMOS, probably 1 gigahertz and below, gallium nitride on silicon carbide above that.
Yeah.
Fantastic, thank you. Question from our attendees here. We work primarily in airborne environments, so liquid cooling may not be a good option. Do you do custom enclosures, or are you focused mostly on rack fit systems?
Usually what we do is 19-inch racks. Okay, it's easier is a standard, is common, and is easy to manipulate.
And so Ryan, I'll build on that. It's a good question. So obviously it really depends on the aircraft. For some of these high power systems that we're doing, the airborne systems we've got on, say, a C-130, that type of aircraft, we have done both air-cooled and liquid-cooled for that particular airframe. Now, if you start talking about fast movers, a solid-state architecture is going to be defined by power per semiconductor device. And certainly we're not here today to say that, the world is over for TWT solutions. It's all about solid state. There are practical considerations, size and power density, particularly as you get higher in frequency, where a tube-based solution certainly still has legs. And I think from my perspective, I'd say if it's on a fast mover, it's on a drone, those sort of concentrated power requirements, this architecture does not lend itself as well to that. But if it's a bigger aircraft, if it's shipboard, if it's land-based, if it's in a tactical trailer, those are all areas where we're having a lot of success with insertion of solid state and replacing a lot of legacy tube stuff.
Okay, great. Some follow-ups. Go ahead.
Specifically about custom enclosure, and sorry there, I want to make sure I answer that directly. The architecture that we have, the way you see that laid out, the one driving for that RF deck, we've got that grooved in a very, very big way. So if we start going kind of off that track into something very unique and very program specific, I mean, we certainly have the technology and the intellect to do it, but we do have to be careful about how many truly unique one customer only things that we do. So it's a little bit of a caution on doing full custom work.
Great, that helps. Follow-up was options for KU band.
It's going to be all about devices, KU band.
Yeah, it's the 11, 13.
Yeah, I think the currently available semiconductor devices, I mean, power per device is not great. So you don't end up with a lot of power per RF deck. I think, as I mentioned, the work we're doing currently is X-band. So we don't have any designs currently that are KU band. And we're definitely not doing any millimeter wave. I mean, Paolo, we use packaged devices.
We use packaged
So
devices.
I guess we're going to be wed to whatever the commercially available packaged semiconductor devices are capable of. And that, like I said, that's where power per device, you start to run out of gas in solid state once you get into those higher frequencies.
Okay, this one might be just a little bit of a go back on the first question. It was more of a, I guess, giving you some more information that in those airborne environments, the customer also has extreme vibe and temp environments. Anything that you can speak to there in terms of your guys' environmental performance?
Yes, we've got it's a land-based requirement, but it's an extreme land-based requirement. And in fact, the shock and vibe, we've got a video on our website. Ryan, we can send you a link later. We've got a video on our website where you can see a 1 kilowatt. In this case, it's an air-cooled amplifier, but it's that same RF architecture. It is transmitting live full power while undergoing 40G shock and vibe. And it was intended to simulate, the customer requirement was to have this kind of electronic warfare and communications platform able to operate on the move inside of an armored personnel carrier. So it's a track vehicle running, full out in a rugged environment. So it's not apples to apples with the airborne mil standard, but it's pretty extreme. And again, that's a proven product that's fielded, been in service for, 5 or 6 years, I guess.
And we have some in airplanes.
Yeah, and otherwise, I guess the short answer is certainly we can do up armored, ruggedized work, and we have the customer base that we support. Go ahead,
even
Paolo.
for liquid cooling too.
Yeah. For liquid cooling, I mean, it comes down to the shock absorbing, the damping, the planning for, even in one of those large cabinets, planning for being able to have that in one application that we have. It's in a tactical trailer that is a moving, relocating, open air range type of application, and it's definitely going to get bounced around out on the range, and so we have planned for that from a mechanical perspective.
Yeah.
Excellent. And just a note to the audience, I just put in the chat the webpage from SMPower RF, which is specific to the testing to MIL standard 810, which includes the video that they referenced. So I'll include that into my follow-up email that goes out to everybody as a resource. Good information about the environmentals that you guys are subjecting some of your current designs to. So I think that's good. Another question here, what is the power level where air-cooled becomes impractical?
Yeah, the problem here is how many fans your ear can support.
Okay. How much noise can you operate with is really the and I'm smiling about that question because it does come up. And yeah, Paolo, it's frequency, it's power. It's not an absolute answer.
There is not an absolute answer. Okay, 8 kilowatts amplifiers air-cooled use about 8 fans. Only on the RF portion, a few fans that are less loud in the controller. Okay, going more than that, I think you may be able to double the power, but that's all. You can't go higher in a pulse amplifier. It is because now you're talking about 16 big fans. The other consequence of that is if you centralize the cooling, you can do that. You can centralize the cooling. Okay, but that becomes almost as complicated as liquid cooler. So yeah, it's not a very easy answer. Okay.
But yeah, I think, and Ryan, can you see the slide? Am I up on air-cooled evolution? Is that showing?
Yes, sir.
Okay, so for everybody, for that question, here on the left, this is very classic, large power combining for air cooled. And to Paolo's point, you've got two big fans on the front of each one of these, and the oh, by the way, is there's two big fans on the back. And so, yes, you can put more 5Us together, but you do have to consider how to combine it, and then what is this structure going to look like when you're done, because you're going up, 5U chassis at a time. And in this particular case with the air cooled, in this, you've got to start adding in power supply decks to support each of those very large boosters. So it just starts to become either physically unwieldy and or from an acoustics point of view, untenable. So Paolo, you'd say, just roughly, 10 kilowatt, 12 kilowatt.
I wouldn't put more than 4 chassis.
Okay. Yep.
4 of those chassis.
Together.
Yeah.
So that's all.
Okay. Good feedback. Another one, can you provide hot swapping in an air-cooled chassis?
That's a little bit more tricky because the fans have to be not obstructed in the back, okay, which makes a backplane way more complicated to do. Okay, do you follow me? You have to have
trying to pulling out these big boosters physically is already very challenging.
Yeah, it's more than 100 pounds.
Yeah, and there's a lot going on back there, and so that one's not nearly as flexible as the 2U. The 2U, to Paolo's point,
50 pounds.
It's plugged into a backplane manifold that just lends itself well to being able to do that. And so I'd say hot swapping is really not a viable option. A replacement is one thing. Hot swapping is another. So can it be field serviced? Yes, it can. Can it be, shoot on the move like we're talking about with liquid cooled? That's a no.
It's much more complex. Okay.
Yeah.
Last question I've got here, and we're just getting close on time, so this is good. If there is any other questions, we do have a few more minutes, but the last one that I have here is, can you provide or are you willing to provide the total cost of ownership model that you showed George and the assumptions that you made?
Oh, yeah. Yeah, absolutely.
Okay.
And what you saw on the slides are accumulation of a Excel spreadsheet that I put together. So I'll take a look at it and see if it's better off just interacting with those who want to look at it, or if it's clean enough to just send it with a simple description of the email. But yeah, I'd love to share that.
Okay.
Yeah.
Well, that's something we can take the action item afterwards for you and I, and then distribute as necessary. So I think that looks to wrap up all the questions that we have, and we're great on time here. So I'm just once again want to remind everyone that we have recorded this and will process this to go out as a video on demand for everybody who is registered and attended, as well as those who weren't able to make it. And you're free to share that content with any of your colleagues or review it again at a later date. We will also include the PDF version of the presentation, along with the contact information for everybody at SMPower, as well as the local Vic Myers team in your territory. So you can reach out for any additional application support, technical questions, or anything that you have on your mind. So with that, I will thank everyone again for your time and participation on the SMPower team from Vic Myers and our customers. Thanks for joining us today on Tech Tuesday.